section 10.4 is calculus and polar coordinates. So last time we worked quite a bit in 10.4 with changing polar into rectangular. We talked about graphing, setting things equal to 0 and solving, things like that with trig, and it was all trig, right? We talked about the fact there wasn't any calculus in that. Well, there's calculus today, so you'll be pleased and excited to know that. We're going to start with some slope stuff. So remember we talked in section 10.2 about parametrics and being able to write things in a parametric way. So we had equations. We're going to have the equation r equals f of theta. And our equations from polar coordinates is that x equals r cosine of theta. But if r is f of theta, then that would be f of theta cosine of theta right here. And y equals r sine of theta, but again, if r is f of theta, then this is f of theta sine theta. And in view of this, we can take these results and we can use the results we had from parametric equations and apply them to polar equations. Okay, so this section is going to be combining some of what we did back in parametrics in 10.2 with what we did in 10.4, polar coordinates, and taking some of those results combined together. So to start with, we're going to talk about the slope of a polar equation. In 10.2, this was the equation we found. There should be a line here, and let me move that again a little bit closer. Down at the bottom of this line, it should say theta equals A, which I can't write small enough. Let me try that one more time. Make my screen a little bit different. A little bit better. I don't have a way to do that inside of equation editor in the computer, so that's actually supposed to be there. So dy dx at theta equal a is dy d theta at a divided by dx d theta at a, as long as dx d theta is not 0. So we did all of that back in section 2, 10.2. And what we're going to do is we're going to combine that with what we know about these equations for x of theta and y of theta that were on my previous slide and are above in your notes. So in particular, you had x is f of theta cosine theta, right? Which is a product. And you had y is f of theta sine theta. So what I'd like for you to do, and I'll write the answers for you when you're done in just a second, is I'd like for you to take the derivative using the product rule of x and y with respect to theta. Okay, so you're going to find dy d theta, and you're going to find dx d theta. Sorry, I wrote it up there as x and y in the opposite order. But you're going to find the derivative of each of these with respect to theta. The product rule. So you're going to have some addition in there. What'd you get for dy d theta? Okay, and I'm going to put the f first just because your book does, not because it matters, but this is what you have, something like that, right? Or maybe you have those terms switched around. You have the f of theta cosine theta in front, either way. What do we get for dx d theta? Does everybody agree with both of those? Okay, great. Now what we're going to do is we're going to use those and combine it with the result above, and we're going to write dy dx as f prime of theta sine theta plus f theta cosine theta divided by f prime of theta cosine theta minus f of theta sine theta. So you're just combining them into one expression using those last two results. Again, as long as the denominator is not 0, then this will hold. right, so any questions so far? Everybody good with that result? Because we're going to use it. We're good with it? All right, our first question that we're going to deal with then, example number 1, is that we have an R equation, R of theta, and it's sine 3 theta. And we're given part A, theta equals pi thirds, and then on part B, we're going to do pi halves. So all of the hard part is not in figuring out what the particular point is, right? That's just the evaluation part, which we worked on last time. It's some trig in there. But the complicated part is going to be setting up and simplifying, if there's any simplifying to do, the particular derivatives that we're working with. So to start with, we need to set up equations for x and y, because we don't even have those yet. So what in the world will x be? Right, and so remember where this is coming from. This is r cosine theta from the last section, and then the r is sine of 3 theta. So this is sine 3 theta cosine, I'm sorry, sine 3 theta, yeah, all right, cosine theta. I'm going to leave some space because I'm going to come back and take the derivative just underneath it. So if you'd like to do the same, that would be fine. So I'm going to leave some space there. Y is going to be r sine theta. So what is y? Right, sine 3 theta, sine theta. Now we're going to take the derivatives of each of these, because if I want dy dx, which is what I'm asked to find at this particular point, then I need to know x prime and y prime, right, with respect to theta. So we're going to find x prime. So what is the derivative of this equation, sine 3 theta cosine theta? Three sine theta what? Well, we are using the product rule, but these are my two pieces, right? Sine of... Okay, so 3 sine theta, and then what? What do we have next? Sorry. Okay. What do you want, Caleb? What do you want me to write?
Okay. I have 3 cosine, 3 theta, cosine theta.
Okay, so on that piece, what you did is you took the derivative of the sine 3 theta, right?
Yes.
Okay, and then what did you do?
Minus the derivative of cosine theta, so minus sine theta, sine 3 theta.
Okay, and then that's the derivative of cosine, which is negative sine. Is everybody good with that piece? You're taking the derivative of 1 and leaving the other unchanged. And yours may be in slightly different ordering. Of course, that doesn't matter. All right, let's do the same thing for y prime then. What's the derivative of sine 3 theta sine theta? Someone else. Caleb did the last one before. Somebody else do this one for me. Thank you, Nidra. Does that look good to everybody? Is that what you have? Excellent. Alrighty, so we have y prime, we have x prime, and we're supposed to be finding, with respect to theta, of course, dy dx. So, dy dx, again, we'll evaluate this at the particular value of theta in a little while, but let's just put this into the correct form, let's say. So we're going to write 3 cosine 3 theta sine theta plus cosine theta sine theta, that's the y prime, over 3 cosine 3 theta cosine theta minus sine theta sine 3 theta. And we want to evaluate this at theta equal to pi thirds. So dy dx at theta equals pi thirds is what's next. Now, as we're working, you might notice that we're evaluating this at pi thirds, and we have some 3 thetas involved. So every time I have a 3 theta, the angle is actually going to become pi. And every time I don't have a 3 theta, it will stay pi thirds. So I'm going to kind of do both of those pieces at once to simplify a little bit as we go. So I've got 3 cosine of pi sine of pi thirds, plus the cosine of pi thirds, sine of, hang on, something I missed. What did I miss? A 3 right here. Did you guys get yours written in? Mine got left out, I'm sorry. So it should be sine of pi at the end. Over 3 cosine of pi thirds, minus sine of pi thirds, sine of pi. Some of this stuff equals 0, correct? What's going to equal 0 in this expression? In a second. All right, so which piece? I'm sorry, say it again for me.
The sine of pi.
Sine of pi, this one's going to be 0. What else is 0? Oh, there's another one below it. Anything else? Just that piece? Okay. So we have then 3. What is the cosine of pi?
-1.
-1. What is the sine of pi thirds?
1/2.
I agree. And then this next piece is going to be 0. I actually could write in, if you wanted to, what the cosine of pi thirds is, which is, I think we've got them backwards, actually. I said I agree, and then I'm not sure that I do. Sine of pi thirds should be square root 3 over 2. Is that right? I'm not remembering backwards, am I?
Sine of pi thirds?
Yeah, should be square root 3 over 2.
Yeah.
Okay. All right, we had it backwards first, but that's okay, no problem. And then my cosine of pi is still -1/2. That cosine of pi thirds is in the denominator now at 1/2. And then I've got minus, again, the sine of pi thirds, then now here's square root 3 over 2 times the 0. So those last two pieces don't necessarily matter. I'm just going to write them in there for consistency so you can see them. If they didn't have times 0, we would need them. We don't particularly need them here, but. What does the numerator become?
-3 out of 3 over 2.
Good. What's the denominator become? -3/2. Thank you. So we can multiply by the reciprocal, right? So this is negative. Well, they're both negative, so those are going to cancel out. This is 3 square root 3 over 2 times 2 over 3 for a grand total of what? Square root 3. So the slope is square root of 3. You can verify, of course, with your calculator on that. Of course, it's not going to give you square root of 3. It's going to give you an approximation, but you could do that to verify. Any questions on that one? Now, on part B, all we're doing is we're changing the angle, which means we don't have to go through all that work again. Agreed? We did it once. There's no reason to start from scratch. So in using this, we're going to be using, and I'll copy and paste it to my slide that I'm working with. All right, so there's the dy dx, and I'm going to be evaluating this at pi halves now. So dy dx at theta equal pi halves. So again, I'm going to simplify a little bit as I go. I'm going to put in the angles. So for the angle where I've got 3 theta, that's going to be 3 pi over 2, right? And the angles where I just have theta are going to be pi over 2. So this is 3 cosine of 3 pi over 2 sine of pi over 2. And then I've got plus cosine of pi halves sine of 3 pi halves over 3 cosine of 3 pi halves cosine of pi halves plus sine of pi halves cosine of 3 pi halves. Thank you. Yes. Right. Something of here is 0, right? What's 0? The cosine of 3 pi halves. These two right here are actually both 0 this time. So I actually have 3 times 0. Again, you don't have to write that part of it. I'm just going to do it so that it's there, but you don't have to. What's the sine of pi halves? 1. What's the cosine of pi halves? It's 0 again, so I didn't even get that one marked. That one's 0. And I've got another cosine of pi halves. It's over here, right? This is 0. What is the sine of 3 pi over 2? It's -1, right? Now, you might sort of be looking at this and saying, okay, the whole numerator is 0, and you're absolutely correct, but we do need to be very careful, because if the whole denominator is 0, this is a problem. So we do have to make sure that we're really going to get 0 on top and not on bottom for this to work. And we will, but we just need to be aware of that. Or do we?
Yeah, you get 0 on bottom too. Unless
No, you.
I think
You wrote it down wrong. It should be sine.
This piece is sine?
Yes.
All right. I said I didn't think I did when I did the notes. All right, good. All right, so what is sine of pi halves? That one's 1, and then sine of 3 pi halves? -1. Good. So we do, in fact, get 0 in the numerator. We get 1 in the denominator, it looks like. Look like to you? So this is going to be 0. So my slope's actually going to be 0 at that particular point. Good catch, guys. All right, any other questions on that one? So this is how we find slopes. We're going to be taking product rule. You're using the product rule for x and y, but you have to start out by defining x and y. X equals this, y equals this based on the R equation. And then you're working with the product rule to establish the quotient, and then you're evaluating, and it works that way for all of them. All right. The next thing we're going to do, and we did this back when we did parametric equations, is we're going to talk about computing area, right? So back in calculus, there's two main things you do. You calculate slope, and you calculate area. Back in Calc 1, they're the very first things you learn how to do. Calculate slope, and you did that with derivatives for quite a while, and then area. So the next thing we're going to compute is area enclosed by a polar curve. Because this graph is not of the form y equals f of x, we can't use the formulas we did. And we could do the same thing we kind of did with slope, where we convert them using the parametric stuff, but there's a simpler approach, and it's to use a geometric argument that we're about to show. Okay? So we're going to use a little bit of geometry. Everything. Trig, now some geometry. It's a good day, right? All right, so here we go. There's a lot for you to write down. So here's what I'm going to do. I'm going to pause this video. I'm going to let you fill in the blanks, and then I'll talk through them with you about what's going on, okay? All right, so the first thing that this talks about is taking the area of a circle. And you remember from geometry, the area of a circle is pi r squared, right? And that's depending upon a certain central angle theta. When I draw my picture here in a minute, you're going to see why this is the case. But instead of actually finding a whole circle, we're going to break it apart into a sector of a circle. So a sector is like a slice of pizza. You guys remember that? So you're imagining taking, I'm not bringing you pizza, no, sorry. But imagine that I did. So you're going to have this little slice of pizza. The pizza slice is going to be determined by an angle. The angle is the measure of the angle of the slice of the pizza, or the slice of the sector. So that angle is theta divided by 2 pi. So theta is the slice of the angle, and then the fraction has theta over 2 pi when you're working to find the actual area of that sector. So the area pi r squared is multiplied by the angle measurement that you're working with, which is theta over 2 pi. And then you end up getting the area of that specific sector. There's a typo there. It should say area is 1/2 theta, or let me say, yeah. Now you get to fix it. Theta r, so r squared theta. All right, so right here should be 1/2 r squared theta. If we multiply right, that's what we get. Okay, so we get that fixed, 1/2 r squared theta. All right, so we're going to consider the area enclosed by the curve that we're working with as r equals f of theta, and we've got raised from theta equals a to theta equals b, where f is continuous and positive on the interval from a to b. And then what we used to do when we were working with functions a long time ago, back in Calc 1, is you made these rectangles underneath curves. Do you remember making rectangles under curves? And you had this sort of image that if you let the rectangles become infinitely many rectangles, or the width of the rectangles going to 0, then you were finding the exact area. Remember, it was a limiting process? We're going to be doing the same thing with this, but we're going to be doing it with sectors. So I'm going to slip to the next slide, but I don't want you to write anything from the next slide. I want you to draw the picture I'm going to do first, okay? So hold off on the trying to fill in the blanks. I promise I'll give you time. I want to draw the picture that correlates to this picture, okay, this slide. So you've got an image of something, so draw yourself a XY axis. I just need quadrant 1 for the purpose of what I'm going to show you. And then draw yourself a curve, something like this. It doesn't have to look exactly like mine. And then imagine that you've got one ray here and one ray here. And these rays are at theta equals A and theta equals B. And you worked last time with drawing different parametric equations, and I hope that you found out that when you dealt with theta equals A, you got a line, and theta equals B, you got a line. I'm working with these rays right here with what I'm doing on this, but you actually would get lines. And what we're going to imagine doing is we're imagine taking a slice that looks like this, so there's a slice, and taking it with a circle like this. So this is my sector. And if we find the area of this little piece right here, and we did this for all of the little slices of sectors, and then we let our sectors become infinitely many, that's equivalent to what we did with rectangles back in Calc 1. We can talk about left endpoint, right endpoint, but as the width of the rectangles goes to 0, it doesn't, not the rectangles, the width of the sectors goes to 0, the width of the angles even. It becomes unimportant whether you're using the left point or the right point to determine the actual radius, right? So it looks like to me at this point, I guess I used the left end point to determine the radius value. All right, so this is the image you have in mind, is filling up this particular area that should look like something anyways, like this, right? This is the actual area that I have. I know, but you can pretend. You can see my shading. So we're going to fill all of that space up. I didn't draw that very well. It shouldn't include the bottom part over here. Let me try that again. It should have only stopped at hit the A value here. All right, so imagine taking and being able to fill all of this area in, but you're filling it in with these tiny little sectors, and the sectors become sort of infinitely small, like our rectangles became infinitely narrow. So the width of each subinterval is then delta theta, which is theta I minus theta I sub 1, or I minus 1 rather. And it's the width B minus A over N. Does that look familiar? Remember seeing B minus A over N back when you did rectangles? Yes, you did. And then on each subinterval, we can approximate the curve by the circular arc radius equals f of theta I. And again, I'm being very generic as to where that theta is being measured because we're going to let this become infinitely small anyway, and then it becomes inconsequential. Then the area A sub I is enclosed by the curve on this subinterval is approximately the same as the area of the sector of radius f of theta sub I. Central angle delta theta. And I believe that this equation down here is written correctly. So we had A sub I equals 1/2 r squared. We had theta before. We're having delta theta now because we're using the central angle delta theta. This is 1/2, and our radius is f of theta sub I. So we're just doing a replacement there with the radius for the f of theta I, which is being squared, times the width of the rectangle delta, or the width of the angle, the measure of the angle delta theta.
What?
1/2 r theta, r squared delta theta, and then 1/2 f of theta sub I squared delta theta. Because r and f of theta sub I are being calculated using the same measurement right here. R is f of theta sub I. And then what we did in Calc 1 is then we took the summation of all of these, right? This is one little piece's area. One little tiny sector's area is what this actually calculates to right here. And then when we did Calc 1, after we found that one little rectangle's area, we added all the areas together. And so that's exactly what we're doing here. The total area, A, enclosed by the curve is then approximately the same as the sum of all the areas. So we're taking the summation from I equal 1 to n of a sub I, and then we're using that formula that we just had on the previous slide of what a sub I is. It's 1/2 f of theta sub I squared delta theta. And if we do this numerous times, that is, if we take the limit as the size gets infinitely small of the angle measure, then we have the limit as n goes to infinity from I equal 1 to n of that measurement, that angle measurement, and that is the integral from a to b of 1/2 f of theta squared d theta. And again, that f of theta is squared because we're talking about a radius, right? This is the radius that we're squaring, and it's this idea of using this area of a circle to do this. What I want you to understand from this argument here is that this argument's doing for polar exactly what the argument back in Calc 1 when you were doing Riemann sums did with rectangles under curves. It's the same argument. It's just doing it with a circle description instead of with a rectangular description because you're doing polar instead of Cartesian or rectangular coordinates. It's the same argument. Okay? So let me pause for a second while you guys continue to write, and then we're going to do a couple of examples of these. Okay, is everyone done with writing this one? Okay. All right, our first example is to take an equation, r equals cosine of 3 theta. Now, you worked with this curve in your last section, which is part of why I'm choosing this particular equation for us to look at now. We did sine of 2 theta in class. I think you did cosine of 2 theta in your homework, but it's the same kind of a curve. You'll need to notice a couple of things. One thing you'll need to notice is it doesn't tell you what those rays A and B are. Do you see that? That means you've got to figure it out. There's several ways you can figure that out. One way is if it's simple enough, you can simply use your calculator to play around with the R value. You know, what does R start and what does it go to, kind of things, until it works out. That actually works okay for this particular equation. It's not going to work very well for number 3 when we do the next example because it's not going to be at a nice, neat whole pi or half pi value. You're just not going to be able to see it very conveniently. So I want to show you in general how you can do it, and then you're welcome, of course, to verify this with your calculator as you're finding what you think is going to happen. So this is going to be one leaf of something that looks somewhat like a rose petal. I mean, that's what you're looking at. Remember when we did those last time? There was different names. I told you to look in your book. It gave you different names for the different kinds of graphs you were getting. This one actually looks like a rose. And the way that this is going to matter is when you're looking at the particular graph, somebody graph it for us and tell me what kind of picture you get. A rose with how many leaves, just so we know. Somebody grab a calculator and do that. Is that the petals are going to happen, they're going to start and end, they're going to completely enclose themselves when we get back to an R value of 0, right? Because at an R value of 0, you hit back at the origin. We worked on that last time. So in particular, what we're going to be looking at is we're going to be looking at where this equation equals 0. And that's, again, part of the reason why in the last section your directions included some pieces where it says find out where in the world does r equal 0. It's for exactly this purpose, okay? So one of the things that we worked on this is that this is all about unit circle questions, right? It's a unit circle issue. Where on your unit circle does the cosine value, or do the cosine values equal 0? Right, all of the half pi values at the top of your unit circle and at the bottom of your unit circle, right? So the angle that you've got on this one is 3 theta, and for the purposes of our argument, we're going to write this at pi over 2, 3 pi over 2, And we could keep going indefinitely. Or if you want to, you could write that this is happening at k pi over 2 plus k pi. I didn't write that right. Pi over 2. There we go, plus k pi. We can't simply write k pi over 2 unless you want to specify that k is odd. And you could do that, I suppose. But typically we let k be an integer, so we need to do k pi. Otherwise we get the even pi values as well, so they'll be not giving us the right places. Now, in particular, then, if we're solving this, what values did this give me? Does this give me for my pi over whatever? What do I get? Pi over 6. What would the next one be? Pi over 2, right? And we could keep going. We could do this in general if you'd like. This is pi over 6 plus k pi, k pi over 3, something like this. The reason I wrote these first two down the way that I did is because we're looking for two specific values, an a value and a b value. And it really is nothing special about the first two. They're just the first two I wrote. So they will work. Every area of this, one of the petals of my rose in this one is going to actually be the same amount of area. It's a symmetric kind of graph, okay? So there's nothing special about using pi over 6 and pi over 2 here. It's simply that they're the first ones listed. Now, what was the image you got? I had a couple of you guys graphing this. What did it look like? A rose with how many petals?
3.
What'd you get, Caleb? 3? 3 petals. So that's coming about partially anyway because this is 3 theta, right? It doesn't quite work that way when I had 2 theta. Do you guys remember when I had 2 theta how many rose petals I had? It was actually 4. It was doubled, yeah. So it doesn't correspond identically with the number on the angle, but it has to do with even versus odd, which your book talked about, I believe, if you did have a chance to read through that. But we actually are using now then the area equals. These values right here are A and B. That's why we did it. They're going to be the angle measures that we're going to use. So I'm going to have 1/2. I'm going to pull the 1/2 out in front. The integral from A, which is pi over 6, to B, which is pi over 2. And I'm supposed to be using my function value squared. Well, my function is cosine of 3 theta. So that means I've got cosine squared of 3 theta. And you're going to get good at trig in this section, just like hopefully you did a little bit in 10.3. One of the things that you need to be able to do is not have that squared there in order to integrate this. And one of your techniques of integration back from Calc 2 had to do with using power-reducing formulas for cosine squared. If you flip to the front of your book, it tells you that the cosine squared can be rewritten in a different way using a power-reducing formula. I can't remember what your book references it at, but it's in the top. It's on the left-hand side of the page. Did you find it, Taylor? I'm sorry, maybe the right-hand side of the page. But on the
1 plus cosine 2 theta over 2.
Okay, so let me write down exactly what you just read, Caleb. Read it for me again. It tells you about cosine squared, right?
Yes.
It's what?
1 plus cosine 2 theta over 2.
Right. And this is a double angle formula as well because you're just turning into a double, right? Double angle. Do you guys see that? Theta becomes 2 theta. So we're going to use this measure, or this, this identity, in order to rewrite my equation. So this is 1/2 the integral from pi over 6 to pi over 2 of cosine of squared. Well, cosine squared is going to be 1 plus cosine of what angle now? 6 theta. I need to double what I had. I had 3 theta, so doubling that would be 6 theta over 2 d theta. It's not a very good looking 6. That's a little better. All right, so we're going to integrate this, which we can now. Before I do that, I'm actually going to, oops, I didn't give myself enough space. Before I do that, I'm actually going to pull that 1/2 to the front, so this is area. So I'm going to write this as 1/4 so that I don't have to deal with it. What's the integral of the 1?
X.
Yeah, it would be x. We're working with theta, so we'll call it theta. And then what's the integral of cosine of 6 theta? That's going to be part of it.
Sine 6 theta over 3.
Right. So I'm going to write it as 1/6 in front, but this is sine of 6 theta. Do you remember why that 1/6 is there? What's really going on? There's a chain rule or a u substitution, right? The u value is the 6 theta, so I'm going to get a 1/6 factor because of it. If you need to write down the u substitution to see that, then write it down. If you don't, then that's fine. And then we're working with the angle measures pi halves and pi sixths. So I've got this 1/4 here. The first angle is pi halves for the theta plus 1/6. And then what is 6 theta times pi halves? I'm sorry, not times, but evaluated at pi halves. What is the 6 times the pi halves? Right, that's 3 pi. Good. And I'm supposed to be measuring this, subtracting pi over 6 plus 1/6. And then when I take the 6 theta and evaluate that at pi over 6, I get sine of pi. Sine of 3 pi, sine of 6 pi, what are those measurements? No. Try again. They're what? Somebody said it. Nathan said it, yeah. Micah. There's 0. Sine of pi and sine of 3 pi is actually the value 0. So this is 0. I didn't mean theta there. 0. There we go. So all I actually end up with is pi halves minus pi sixths times my 1/4. So what is pi halves minus pi sixths? One half minus 1/6, guys. Pi over 3 is correct. It's 1/3. And then times my 1/4 is going to give me pi over 12. Any questions on that? You're welcome to verify with your calculator. That's perfectly fine. But your calculator, of course, will give you an approximation. All right, I would like to at least take a moment to solve this for theta. I think we have time to do that. So just like on the last one, we're going to get a full loop, and you can take a look at the calculator and how this works to give you the larger loop to make sure that you're actually getting the larger one versus the smaller one, which is a calculator issue. But we're going to be doing this with setting this at equal to 0, just like we did a moment ago. So if I'm trying to set this equal to 0, I can subtract my 1 and divide by 2, and I find out that sine of 2 theta is supposed to be negative 1/2, right? And we get lots of different values for this. Somebody tell me one value, one angle measure where we have a sine of negative 1/2. You should be thinking unit circle here. In radians. Now, let me pull up what you just said before, because you said negative 30 degrees is one of the things I heard you say, or heard somebody say. Somebody said negative 30. If you're taking a look down here in quadrant 4, this is negative 30. What is the angle measure for negative 30 in radians? No. Let's do negative pi over 6. That's one way to deal with it. There is one over here, Ben, that's 7 pi over 6, and that's actually the next one. So 7 pi over 6. We could continue around and say that we've got another one at 11 pi over 6, right?
Negative pi over 6 doesn't work for negative 1/2.
What's that?
Negative pi over 6 didn't work for getting negative 1/2. I got negative radical 3 over 2.
For your sine value?
Yeah, sine of 2 times negative pi over 6.
But I don't have anything, I haven't done anything with the 2 yet.
Oh.
I'm just doing a sine value. So if you typed in sine of negative pi over 6, I think you're going to get negative 1/2.
Let's try that.
Okay, because we haven't dealt with the 2 part of it yet.
Gotcha.
Okay, now that I have this, I can actually divide it by the 2. So this is actually negative pi over 12 and 7 pi over 12. And this is why I was mentioning before that we're not going to be able to just graph this and guess that I'm getting pi over 12 values that will hit back at the right place. mean, pi over 12 is not something we work with quite often. So that's not going to be a particularly helpful value. But we can verify now that we're getting these values that this would actually give me my larger loop by using your calculator, that it doesn't give me a smaller loop. This is one that's got the loop inside of the loop, if you guys remember that or not. That's what you're going to get if you do your calculator. So we're going to just write this down. This means that when I do my angle measurement over here, my lower value is negative pi over 12. That doesn't look good at all. Negative pi over 12, and my upper value is 7 pi over 12. And then I'm going to actually have to take the 1 plus the 2 sine of 2 theta, and I'm going to have to square it. And that's where we'll pick up next time, is squaring that.